In literature, authors like Philip K. Dick and Michael Crichton have used parallel universes to craft intricate narratives that challenge our perception of reality. Television shows have embraced this concept with enthusiasm. Series like Fringe and Rick and Morty use parallel universes as central plot devices, allowing characters to travel between different versions of their world. These shows often use the concept to explore themes of identity, free will, and the nature of existence itself. In cinema, parallel universes have been featured in blockbuster films such as The Matrix and Interstellar. These movies use the concept to create mind-bending plots and visually stunning representations of alternate realities. Comic books and graphic novels have also extensively explored parallel universes, with major publishers creating entire multiverses where different versions of familiar characters coexist. While parallel universes remain firmly in the realm of science fiction, they have also influenced scientific thought. Some physicists have proposed theories that suggest the existence of parallel universes as part of a larger multiverse. These ideas, while speculative, demonstrate how concepts from science fiction can inspire and influence scientific inquiry, blurring the lines between imagination and theoretical physics. Parallel universes have captured the imagination of scientists and the public alike, but they are often misunderstood. One common misconception is that parallel universes are exact copies of our own, differing only in minor details. In reality, if parallel universes exist, they could be vastly different from ours, with entirely different physical laws and constants. Another misconception is that we could easily travel between parallel universes if they existed. However, even if parallel universes are real, the barriers between them would likely be insurmountable with our current understanding of physics. The idea of hopping between universes remains firmly in the realm of science fiction. Many people also believe that the existence of parallel universes has been proven. In truth, while some interpretations of quantum mechanics suggest their possibility, there is currently no concrete evidence for parallel universes. What if the universe isn't alone? What if there's another, right beside us, and we never even knew? In the heart of quantum mechanics, a theory emerged, wild, defiant, and beautiful. The many worlds interpretation. It claimed every choice, every chance, splits reality in two. A million versions of you scattered across the cosmos like echoes in a canyon. Some universes may be almost identical. Others, twisted, broken, strange. Physicists once laughed, but then, evidence. Particles behaving as if they're in multiple places at once. Could time flow backwards there? Could stars burn in colors we've never imagined? A parallel universe is a hypothetical realm that exists alongside our own, potentially containing alternate versions of reality. These universes might have different physical laws, historical events, or even variations of ourselves living different lives. The concept stems from various interpretations of quantum mechanics and cosmological theories. Scientists propose that parallel universes could arise from the many worlds interpretation of quantum mechanics. This theory suggests that every possible outcome of a quantum event occurs, each in its own separate universe. For instance, in one universe you might be reading this explanation, while in another you decided to watch a movie instead. Another idea posits that parallel universes could exist as separate bubble universes within a larger multiverse. These bubbles might occasionally collide, potentially leaving observable effects in our cosmos. Some researchers even speculate that mysterious cold spots in the cosmic microwave background could be evidence of such collisions. While parallel universes remain theoretical, they captivate scientists and the public alike, offering mind-bending possibilities about the nature of reality and our place within it. The search for evidence of their existence continues, pushing the boundaries of our understanding of the cosmos. Parallel universes and alternate dimensions are often confused, but they represent distinct concepts in theoretical physics and cosmology. Parallel universes, also known as the multiverse theory, suggest the existence of countless other universes besides our own. These universes might have different physical laws, different versions of events, or even different versions of ourselves. The idea stems from quantum mechanics and the many worlds interpretation, which proposes that every possible outcome of a quantum event occurs in a separate universe. Alternate dimensions, on the other hand, refer to additional spatial or temporal dimensions beyond the four we experience in our everyday lives, 3 of space and 1 of time. String theory, for instance, proposes that our universe might have up to 11 dimensions, most of which are imperceptible to us. These extra dimensions could be tightly curled up at every point in our familiar 4-dimensional spacetime. The key difference lies in their nature and implications. Parallel universes are complete, separate realities, while alternate dimensions are additional aspects of our single reality. Parallel universes might contain entirely different versions of our world, whereas alternate dimensions could explain phenomena within our universe, such as gravity or dark matter. Scientists continue to explore both concepts, seeking evidence and developing theories that might one day bridge the gap between quantum mechanics and general relativity. While both ideas challenge our understanding of reality, they offer exciting possibilities for explaining the mysteries of our cosmos and potentially opening doors to new realms of existence. Several scientific theories lend support to the intriguing concept of parallel universes. The many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett, suggests that every possible outcome of a quantum event occurs in a separate universe. This theory posits that our universe constantly branches into countless alternate realities, each representing a different outcome of quantum interactions. String theory, a framework attempting to unify fundamental forces, also hints at the possibility of parallel universes. It proposes that our universe might be just one of many brains floating in a higher dimensional space. These other brains could be entire universes with their own physical laws and properties, existing alongside our own. The concept of eternal inflation in cosmology provides another avenue for parallel universes. This theory suggests that the inflationary period of the early universe never completely ended and continues to create new bubble universes with potentially different properties. Our observable universe might be just one of these bubbles in a vast multiverse. These theories, while speculative and not yet proven, offer tantalizing possibilities for the existence of parallel universes. They challenge our understanding of reality and push the boundaries of what we consider possible in the cosmos. The concept of parallel universes has roots in both scientific thought and philosophical speculation, but its modern formulation in physics can be traced back to Hugh Everett III in 1957. Everett, then a graduate student at Princeton University, proposed the many worlds interpretation of quantum mechanics as part of his doctoral thesis. Everett's revolutionary idea suggested that every time a quantum event occurs, the universe splits into multiple versions, each representing a different possible outcome. This interpretation was a radical departure from the prevailing Copenhagen interpretation of quantum mechanics, which posited that quantum states only collapsed into a single reality when observed. While Everett's ideas were initially met with skepticism, they gained traction over time and influenced subsequent theories in quantum mechanics and cosmology. His work laid the groundwork for later concepts like the multiverse theory, which proposes the existence of multiple universes beyond our own. It is worth noting that parallel universes had appeared in science fiction and philosophical thought experiments long before Everett's formal proposal. However, His work marked the first serious scientific consideration of parallel universes as a potential explanation for quantum phenomena, bridging the gap between speculative fiction and theoretical physics. The idea of parallel universes has undergone significant transformation in scientific circles over the past century. Initially dismissed as mere science fiction, it has gradually gained traction as a serious scientific concept. This shift began with the development of quantum mechanics in the early 20th century, which introduced the notion of quantum superposition, suggesting particles could exist in multiple states simultaneously. Hugh Everett proposed the many worlds interpretation of quantum mechanics in the 1950s, positing that every quantum event creates a branching of reality into separate universes. This marked a pivotal moment in the scientific consideration of parallel universes. While controversial at first, Everett's ideas slowly gained acceptance among some physicists and cosmologists. In recent decades, string theory and the concept of the multiverse have further expanded scientific thinking about parallel universes. String theory suggests our universe might be one of many brains floating in a higher dimensional space. The inflationary model of the Big Bang, proposed by Alan Guth, also supports the possibility of multiple universes, each with potentially different physical laws. Today, the concept of parallel universes is an active area of theoretical physics and cosmology. While still lacking direct observational evidence, it has become a respected scientific hypothesis explored through mathematical models and thought experiments. This evolution reflects the ongoing interplay between theoretical physics, observational cosmology, and our understanding of the fundamental nature of reality. Quantum mechanics forms the foundation for many theories of parallel universes. At its core, quantum mechanics describes the behavior of particles at the smallest scales, where strange and counterintuitive phenomena occur. One of the most intriguing aspects of quantum mechanics is the concept of superposition, where particles can exist in multiple states simultaneously until observed or measured. This idea of superposition extends to the many worlds interpretation of quantum mechanics proposed by physicist Hugh Everett. According to this theory, every time a quantum event occurs, the universe splits into multiple versions, each representing a different possible outcome. These splits create an ever-expanding tree of alternate realities, effectively giving rise to parallel universes. Another quantum mechanical concept that supports the idea of parallel universes is quantum entanglement. This phenomenon describes how particles can become interconnected in such a way that the state of one particle instantly affects the state of another, regardless of the distance between them. Some theories suggest that entanglement could potentially connect our universe with others, forming a vast multiverse of interconnected realities. Quantum fluctuations, tiny variations in the amount of energy in a point in space, also play a crucial role in theories of parallel universes. These fluctuations are thought to have given rise to our own universe during the Big Bang, and some cosmologists propose that they could continually create new universes in a process called eternal inflation. This would result in a multiverse containing an infinite number of parallel universes, each with potentially different physical laws and constants. The multiverse theory and the concept of parallel universes are closely intertwined, often considered different aspects of the same overarching idea. At its core, the multiverse theory proposes that our universe is not alone, but rather one of many universes existing simultaneously. These multiple universes are sometimes referred to as parallel universes. In this context, parallel universes are thought to be separate realms of existence, each with its own set of physical laws, constants, and potentially different versions of reality. These universes might be nearly identical to our own, differing only in small details, or they could be radically different with entirely unique properties and structures. The multiverse theory suggests several possible types of parallel universes. One version proposes that every quantum event creates a new universe, resulting in an infinite number of branching realities. Another interpretation envisions a vast cosmic landscape where different universes bubble up and exist alongside each other, like soap bubbles in a foam. While the multiverse theory remains speculative and currently unprovable, it offers intriguing possibilities for understanding the nature of our reality and addressing fundamental questions about the origins and structure of the cosmos. As scientists continue to explore these concepts, the relationship between the multiverse theory and parallel universes remains a fascinating area of theoretical physics and cosmology. The many-worlds interpretation is a fascinating concept in quantum mechanics that challenges our understanding of reality. Proposed by physicist Hugh Everett in the 1950s, this interpretation suggests that every time a quantum event occurs, the universe splits into multiple parallel realities. In the quantum world, particles can exist in multiple states simultaneously, a phenomenon known as superposition. When we observe or measure these particles, they seem to collapse into a single definite state. The many-worlds interpretation proposes that instead of collapsing, all possible outcomes actually occur, each in its own separate parallel universe. This means that for every decision we make, every quantum event that happens, a new universe branches off. In one universe, you might have chosen to wear a blue shirt today, while in another, you opted for red. These parallel universes are thought to be identical to our own, except for that one difference resulting from the quantum event. Critics argue that this interpretation leads to an infinite number of universes, which some find difficult to accept. However, proponents argue that it elegantly solves many paradoxes in quantum mechanics without requiring additional assumptions. The many-worlds interpretation remains a topic of intense debate and research in the scientific community, pushing the boundaries of our understanding of reality and the nature of the universe itself. Parallel universes have captured the imagination of both creators and audiences in popular culture and science fiction for decades. This concept allows storytellers to explore alternative realities, what-if scenarios, and the consequences of different choices. They remain a fascinating theoretical concept rather than an established scientific fact. Lastly, there is a misconception that parallel universes, if they exist, would solve the problem of quantum uncertainty by realizing all possible outcomes. While this idea, known as the many-worlds interpretation, is one way of understanding quantum mechanics, it is not the only explanation and is still hotly debated among physicists. In a parallel universe, the fundamental laws of physics could be radically different from our own, leading to a reality that might be difficult for us to comprehend. One possibility is that the strength of gravity could be altered. If gravity were significantly stronger, stars and planets might form more rapidly, and the universe could be much more compact. Conversely, weaker gravity could result in a universe where matter struggles to coalesce, potentially preventing the formation of galaxies as we know them. The speed of light, which is constant in our universe, could vary in a parallel realm. This change would have profound implications for the nature of space and time, potentially altering the very fabric of that universe. Similarly, the strong and weak nuclear forces which govern the behavior of subatomic particles could have different strengths or operate in entirely novel ways. Another intriguing possibility is a universe with additional spatial dimensions beyond the three we experience. This could lead to bizarre physical phenomena and forms of matter unlike anything in our cosmos. The laws of thermodynamics might also differ, potentially allowing for perpetual motion or negating the concept of entropy altogether. Perhaps most mind-bending would be a universe where cause and effect are not bound by time as they are in ours. Events could precede their causes, or multiple contradictory outcomes could coexist simultaneously. Such a reality would challenge our fundamental understanding of logic and causality, showcasing just how strange and wondrous parallel universes could be. In our universe, the speed of light is a fundamental constant, unwavering at approximately 300 million meters per second in a vacuum. However, in a hypothetical parallel universe, this cornerstone of physics could potentially differ, leading to profound consequences for the fabric of space and time. A parallel universe with a faster speed of light might experience more rapid information transfer and energy propagation. This could result in a cosmos where events unfold more quickly and distant parts of the universe remain more intimately connected. Conversely, a universe with a slower speed of light might appear more sluggish, with greater delays in cause and effect relationships across cosmic distances. The implications of a varied speed of light extend beyond mere travel times. In such a universe, the relationship between mass and energy, famously described by Einstein's equation, could be fundamentally altered. This might lead to different rules governing the formation of matter, stars, and even life itself. Moreover, a change in light speed could affect the universe's expansion rate, potentially resulting in a cosmos that evolves differently from our own. It might expand faster or slower, or even experience different phases of expansion and contraction. These variations underscore the delicate balance of physical constants that shape our reality and hint at the vast possibilities that might exist in other universes. The concept of parallel universes with different numbers of spatial dimensions is a fascinating possibility in theoretical physics. Our familiar universe has 3 spatial dimensions plus time, but some theories suggest that other universes could indeed have different dimensional structures. String theory, a prominent framework in theoretical physics, actually requires the existence of extra dimensions beyond the 4 we experience. These additional dimensions are typically thought to be compactified or curled up so small that we cannot detect them. However, in the context of parallel universes or the multiverse, these extra dimensions might manifest differently. Some models propose that parallel universes could have any number of spatial dimensions, from as few as 1 or 2 up to 10 or even more. In a universe with only 2 spatial dimensions, for instance, life as we know it could not exist. Gravity would behave differently, and complex structures like atoms might be impossible. Conversely, universes with higher numbers of dimensions could have physics and properties wildly different from our own. They might allow for phenomena that seem impossible in our 3-dimensional space, such as the ability to see all sides of an object simultaneously. While these ideas remain speculative, they highlight the potential diversity and strangeness of parallel universes, pushing the boundaries of our understanding of reality itself. In a parallel universe where gravity behaves differently, the very fabric of reality would be fundamentally altered. Imagine a cosmos where the force of gravity is significantly stronger. Planets and stars would form much more rapidly, potentially leading to a universe dominated by enormous, ultra-dense celestial bodies. These cosmic giants would exert such powerful gravitational forces that light itself might struggle to escape their grasp, resulting in a dark, compact universe filled with black holes. Conversely, if gravity were weaker, the formation of large-scale structures like galaxies and solar systems could be severely hindered. Stars might not be able to compress hydrogen sufficiently to ignite fusion, leaving the universe cold and dim. Planets, if they managed to form at all, would likely be unable to hold on to their atmospheres, making the development of life as we know it nearly impossible. A universe with inconsistent gravity could be even stranger. Regions of space with varying gravitational strengths could create cosmic patchworks of dense matter clusters alongside vast, empty voids. In such a reality, the predictable orbits and rotations we observe in our universe would be replaced by chaotic, ever-changing celestial dances. The implications of altered gravity extend beyond cosmic structures. The fundamental forces of nature are intricately balanced in our universe. A significant change in gravity could disrupt this equilibrium, potentially altering the behavior of subatomic particles and the formation of basic elements. This could result in a universe with entirely different chemical properties, where the periodic table as we know it might be unrecognizable. The strong and weak nuclear forces, 2 fundamental forces of nature, exhibit markedly different behaviors. The strong nuclear force, as its name suggests, is incredibly powerful but only operates over extremely short distances. It acts primarily within the atomic nucleus, binding quarks together to form protons and neutrons, and holding these particles tightly within the nucleus. This force is so intense that it overcomes the electromagnetic repulsion between positively charged protons, allowing atoms to maintain their structure. In contrast, the weak nuclear force operates on an even smaller scale and is significantly less powerful than the strong force. Despite its relative weakness, it plays a crucial role in radioactive decay and nuclear fusion processes. The weak force is responsible for the transformation of neutrons into protons, a process known as beta decay, which is essential for the stability of certain atoms and the energy production in stars. Another key difference lies in their range of influence. While the strong force rapidly diminishes beyond the confines of the atomic nucleus, the weak force, though less intense, can extend slightly further. This difference in range contributes to their distinct roles in particle interactions and nuclear processes. The behavior of these forces also differs in terms of the particles they affect. The strong force acts on particles called hadrons, which include protons and neutrons, while the weak force interacts with all known fermions, including electrons and neutrinos. This broader scope of interaction allows the weak force to play a unique role in particle physics and cosmic phenomena, despite its relative weakness compared to the other fundamental forces. The concept of parallel universes opens up intriguing possibilities for the fundamental nature of reality. In our universe, we have identified a set of elementary particles that form the building blocks of all matter and energy. However, in parallel universes, the rules could be entirely different. Theoretical physicists propose that parallel universes might indeed have different sets of elementary particles. These alternate particle families could lead to radically different physics, chemistry, and even forms of life, unlike anything we can imagine. In some parallel universes, there might be additional types of quarks or leptons, or perhaps entirely novel categories of particles that do not exist in our reality. The laws of physics themselves could vary between universes, potentially altering the way particles interact or even changing the number of fundamental forces. In one universe, there might be an extra force beyond the four we know, while in another, gravity might not exist at all. These differences at the particle level could cascade into large-scale effects, creating cosmos with properties vastly different from our own. Understanding these possibilities not only stretches our imagination, but also helps scientists explore the limits of our current theories. By considering how things might be different, we gain new perspectives on why our universe is the way it is, potentially uncovering deeper truths about the nature of existence itself. In a parallel universe where electromagnetism has a different strength, the very fabric of reality would be fundamentally altered. This change would have profound effects on the structure of atoms, the formation of molecules, and the behavior of light. Stars might burn hotter and faster, dramatically changing the course of stellar evolution and the production of heavy elements, for the development of structures in the universe, from galaxies to planets. The fundamental constants of nature play a crucial role in shaping the universe as we know it. Any changes to these constants could dramatically alter the formation of matter, potentially leading to a vastly different cosmic landscape.
This has been a Pinguinati production. Thanks for watching. Subscribe for more videos. If you'd like to support the channel, links are in the description.